Okay. Hi, everyone. My name is Ryan, and today I'm going to be talking about two different analysis techniques performed on a similar task, and what we can learn about the time course of information processing through both ERP and machine learning classification analyses. But first, I want to outline the cognitive theory underlying our questions. So how does the brain build a memory for a visual event? So we know from ERP analyses that the time course of information processing is important to consider. So for example, when you look at an average ERP waveform, you'll see some early visual components like the P1 and N1 versus later higher level cognitive components like the P2, N2, and P3 that can be more associated with target selection and even target encoding. And all of these play an important role in understanding how a visual memory is built. However, we also know that the way information is presented can matter as well. So for example, if a target is presented in a rapid serial visual presentation format such that it's masked by distractors, or presented in isolation in what we're calling a skeletal display, you can see that the time course of the P3 changes based on the format, where it's occurring faster in the skeletal display, presumably because there's less visual interference and a greater ease of selecting the target for later encoding. However, while ERPs are great for correlating cognitive mechanisms to EEG data, it says nothing about what the actual underlying information representation could be. So what is actually it within the component when that component is being activated. However, neural decoding analyses can correlate item-specific information with underlying neural activity, and they've been growing rather popular in cognitive neuroscience with the increased computational abilities that we now have. So you can see in this study, the classifier was trained to distinguish a set size 2 versus a set size 6 memory display. I mean, it can do so both during early sensory stages, early visual stages, as well as during a maintenance period. So what would happen if we apply this machine learning analysis to the presentation format that we had previously discussed, an RSVP versus a skeletal display? So if we considered that a classifier was detecting early visual effects, we might expect that during the skeletal stream, it would show high classification early on compared to the RSVP, which would have a rather decreased and shortened time course due to the onset of visual distracting information. However, and a rather paradoxical prediction is that because the stimuli are masked and the task is more effortful and difficult to complete, information will need to be held longer within the brain. And this could actually increase the time course of classification accuracy during RSVP, as that information needs to be maintained more effectively to be able to complete the task. And so this is what we predict we would actually see in our classification analyses. So in the current study that I will highlight, we had participants complete 2 different presentation formats while EEG data was recorded. So first, in the skeletal or single presentation stream, participants were to detect one target, either a face or a body that was not followed by any distractors, compared to an RSVP stream where a target, again, either a face or a body shown for the same amount of time, was now flanked both by distracting chair pictures as well as a highly salient visual mask. And then across both task, participants had to report the exact identity of the target. So behaviorally, what we can see is that the RSVP task was in fact more difficult, as participants were less accurate in completing the task for identifying the item, but just about as accurate for identifying the category. And we also see replications of the ERP analyses shown previously. So the P3 has an earlier onset latency for the skeletal display format as opposed to the RSVP format. You'll also notice in the RSVP an oscillatory effect. This is evidence that the distractors are being detected by early visual processing as well, creating an SSVEP, or steady state visually evoked potential. This is very common and can be thought of as little N1, P1 complexes occurring. So again, the distractors are attracting visual processing. So if we imagined that the classifier was picking up on this P3 difference, that we might see stronger classification accuracy in the single, what we in fact see is an equal time course of classification accuracy between both the skeletal and RSVP processing streams. Thus, the information that's represented in the brain for these different cognitive mechanisms is approximately the same amount of time, regardless of the presentation format, which is very interesting because even though the information that can distinguish faces versus bodies is probably undergoing different processing at each time, it's occurring for around the same amount of time. So it's rather mechanism invariant for the classifier. I mean, if we compare the actual time course between ERP and decoding, we can see that while there is a significant latency difference in ERP, there's no difference in SVM, and the difference between the latency difference between the two analyses is also significantly different. So finally, we used one last classification technique, temporal generalization, which can reveal novel insights about whether the information signal changes dynamically over time, such as this chain activation, which would be so high accuracy across the diagonal when the training and testing is at the same time point, versus a rather sustained activation where even when testing at different time points during the study, the activation remains significant over time. And what we can see from our two temporal generalization plots is what looks like a really strong diagonal for both presentations, but when we assess each classification point for significance, we see a much stronger dynamic representation in the RSVP stream compared to the skeletal stream, which shows some dynamic processing or dynamic representations, but a slightly more sustained activity as well. So to conclude, as we view visual information to remember for future use, signals from the brain can be analyzed using various techniques. From our results, the ERPs and classification seem to tell us two different sides of the information processing story. ERPs highlight the early onset of encoding in single/unmasked information because of the pop out of the target and ease of selection. But in classification, though we theorize different time courses, there's no measurable difference that can be decoded in the brain. So these differences highlight the importance of utilizing both analysis techniques. ERP research is not done yet. ERPs can highlight the cognitive control mechanisms that information undergoes, but is rather information invariant. And contrary to that, neural decoding analyses can detect the information representation over time, but is rather mechanism agnostic. It doesn't matter where in the visual stream that information is being processed, so long as it can be used to detect the difference between a face trial versus a body trial. So it's important to interpret both of these analysis techniques to get a fuller picture of the story. So thank you for your time. And I want to give a special thanks to everyone in my lab who's helped with this project, as well as the RAs who helped during the data collection, and all the participants who participated in this study. So thank you, and I will take any questions.
Okay, thank you, Ryan, for the interesting talk. We can take questions now from the audience. Okay, so you find that, let me ask one question. So when you do the ERP analysis, do you compare the face and body conditions?
I have looked, and I actually do have that data here.
Like, so this, okay, so, oh, okay. Can you explain this now?
Yes, and we have never analyzed this for significance, but it looks like there are slight differences in the PZ or electrode for whether a face or a body was presented in either presentation format. So you can see potentially an increase in amplitude for the P3 component, and it may be a slight latency shift. And this would be what the classifier is picking up, but it's also important to take into account that the classifier is being trained across all 28 used electrodes. So even if we see differences just at this electrode, it may not be, this isn't the full picture that the classifier is picking up on.
So can you explain, like, what do you classify in your classification analysis? What are the conditions that you're classifying?
So we do a within presentation format classification where we train the classifier to detect either a face trial or a body trial. And then we test on, so it's a 90-10 test split.
Okay.
So,
because what you show me here is that, like, your ERP that cannot show the difference between the body and face, but your classification can show, right? Because you have a higher classification accuracy.
Correct, yes.
So maybe I'm confused, but like, what do you compare when you compare ERP analysis and classification? What are they comparing the same, like are trying, for example, in the classification, you're trying to do a classification between two conditions. Do you do the same in ERP or no? That's something else.
Yes. So it is a little, it's a little confusing to think about what the comparison between the analyses would be. We're doing the latency of the area under the curve between the two techniques. So what's the 50% latency for the P3 component in the PZ electrode versus the latency of the classification, and that latency difference is what we're saying shows an early onset in ERP, but not for classification. I'm not sure if that answers your question.
I'm asking this because, like, in my experience, I usually find that classification analysis finds even subtle differences between conditions, whereas like in ERP, it's very difficult to get that, right? Like, so I find that the classification analysis is more sensitive to condition, to the like comparing conditions. So I wasn't quite sure why you don't see that in your analysis.
That's a good question. It could be because we're using single trial data. So I've seen that a lot of classification papers bin their trials, create little mini blocks. We actually found in our pipeline that didn't didn't show classification as we expected. It was rather oscillatory, and we just think that was noise. And we actually found a more coherent classification in single trial, but because it's a lot noisier, that could be where the difficulty is there. I don't honestly know why the mini blocking didn't work. I've tried asking researchers about it, and they seem shocked as well. So if you have any insights, I'd love to hear them.
Sure. Like as I said, like I need to know more about like your conditions, like what you're classifying. Then I would be happy to give you more feedback. And very interesting results, by the way. We have more questions from the audience, so I would like to ask them before like we are done with time. So Ilya asked, did you do any feature selection in order to potentially increase accuracy?
No, we did not. We tried to keep it as simple as possible to minimize fitting.
Okay. Or do you use all electrodes? I'm not familiar with which electrodes time points are best for memory. So, okay. So feature selection could help also classification accuracy. Then another question from Chloe. Did you do any classification of the distractors to see if representations are held at all in the RSVP paradigm?
That's a great question. And no, we haven't tried that yet. But we have a lot of time in this pandemic. So we could certainly test it out. We've also considered just classifying the exact presentation format, but we suspect that accuracy would be rather high for that as well.
Okay. Another question from Catherine. Interesting results. Do you think the ERP would also be information agnostic to other modalities of sensory information, such as vibration-based electrical tactile stimulation?
That's a great question. It is out of my area of expertise. I would need to test it to be able to give you an answer that I feel comfortable sharing with a crowd. But I guess I can say perhaps it's worth testing for sure.
Okay, so I think we are done with